So my talk is going to be slightly different from previous talk. It's mostly on the research, but so the idea starts from about 2 years ago, where I was in an event similar to this with a bunch of researchers from top frontier labs, and we were, as researchers do, trying to predict future. And we had 2 questions at the time. 2 questions. One is how long is going to take the agents do more than 90% of our coding. The second one is how long the agent's going to take to do more than 90% of our general research. And for the coding, we had a kind of estimate of 2 to 5 years at the best and more than 5 years on average. And for kind of our end-to-end research, it was more than kind of 10 years. We were kind of wrong on the coding, maybe not that much, but I'm going to show you we were maybe very, very wrong on the. This is my talk. I've been trying to answer this question of how long can language model do end-to-end research. My background is in security, so I'm going to focus on the security research, but some of these things might apply on other kind of research too. So yeah, I don't mean, by using LLM research, I don't mean using LLM as a tools. As we know, many of the conferences, even security conferences, which are very, very conservative, allow you to some extent to use LLMs. And what I want to do is doing full end-to-end research, like from idea, having hypothesis, coming with a methodology to testing, and go beyond. And you might already have some answers here. Many people disagree. Many people have a lot of doubts. And this is, many people think this is impossible. I was one of them maybe 2 years ago. But I'm going to show you maybe we need to change that slightly. This week, actually, we published this work that we showed Claude can do cryptographic analysis. In particular, I'm going to focus on a specific part of it. What I mean by cryptographic analysis here is you can find flaws in kind of cryptographic algorithms. And one of the works that we have is a small, we find a new attacks on a symmetric crypto algorithm called AES. But I'm going to show you this attack is not possible to, I don't have the capability of doing this attack. And we have 2 authors here, me and Nicolas Carlini. And this is kind of the academic record of us. Nicolas Carlini does a background in system security and recently on machine learning security. My background is on network security and now machine learning security. And 2 of us, plus a copy of internet, plus a bunch of coding agents, shouldn't be essentially able to kind of come up with an attack on a cryptographic systems. While we both like cryptographic a lot, we have tried to break simpler things before, this is very, very big. And to kind of maybe to give a background on what is the actual AES and how does it work, if you ever used internet, you use the AES. But it's a very, very kind of interesting algorithm. It's been standardized in 2001 by NIST. And it's an iterative algorithm that has 10 rounds. Essentially, it gets an input and a key from you or from a program. And then it kind of it has 4 main parts. One is called substitution, the other one called, and the other ones is like do some permutation. What substitution box does, it gets an input and maps it to another set of outputs. And then kind of moves those bits around and add the function of the key that you add to the input. And it's an iterative algorithm. What it means is like it tries to do this thing multiple times. And in the simplest forms of AES, it does this kind of around 10 times. And just for clarification, we didn't break AES. If someone breaks AES, kind of they break internet. So it's a very academic work that I'm going to present. But in particular, we focused on a shorter, like a reduced round AES. Instead of doing the full 10 rounds of AES, we do 7 rounds. This is something that like, academics usually study because it is easier. It might be possible to get some improvement. And when you want to attack 7 rounds of AES, the dumbest algorithm that exists that brute force every key, it's the computation complexity is around 2 to the 128 of operations, which is gonna take us more than the time that our sun is going to nova, so it's not possible. our best algorithm that exists that came in 2013, it takes around 2 to the 99. So maybe in like 200,000 to 200,000 years or something like that, you're gonna finish it. And it's not for lack of trying. There are several works in this area, and they try to break this. It's a fairly well-studied problem. And we have this number now that we showed that we have an attack that can do this break on this reduced round AES in 2 to the 89, or kind of something like that, depends on how you actually count it. And it's around, and we actually did some empirical evaluation, it's around like 200 to 800 times faster. So maybe in like around like 1,000 years. So I don't know how much important that is, but like, yeah. So how does this actually work? So the way that attacks on crypto algorithms usually work is they try to find a relationship between input and output without actually you trying to kind of run the algorithm itself. And in particular, AES uses a specific formula to do this, like substitution, that takes an input, inverts it in some field, and then scales it and shifts it. So assume you have an object, and you kind of scale it and shift it. What it remains is the ratio between this like shape is still the same, just shifted and zoomed in. So like the model understood that AES Sparks has this property and uses this to kind of come up with the algorithm. It's a very, very complicated method. I'm trying to kind of give a summary of it in 2 minutes. So if you are interested, go read the paper. And it's actually, we showed that this is not just AES. We can have attacks on other crypto systems, such as Hawk and Leah, which both are kind of used. Hawk is one of the post-quantum algorithms. Leah is used in like other countries. And none of these attacks have actually changed anything in the internet, but like these are academic achievements. And so hopefully you have an idea that's how does the attack, kind of what is the attack. And I'm going to kind of give you an idea of how we actually did this. So if I wanted to do this, I would have sat somewhere, try to think for a few weeks, come up with a few ideas, then go talk to a few people, and then maybe we come up with a few of the ideas and then go implement them. But how the model does this is slightly different. They come with a lot of ideas, and instead of go talk to people, they try to go implement all of them and to see which one is actually working. And maybe we had this kind of saying before that ideas were cheap and the execution is everything. Now is maybe ideas is more important, and the execution model can do it very, very fast. In particular, for AES, it's hard to do execution because, as I showed, the complexity of it is like more than we can have. So we cannot just go implement to the 89 or whatever algorithm. So instead, we have this harness, which is, I don't think it's kind of very important, but you need to have a harness right now for the models to kind of not go implement everything. So maybe in future you don't need this, but right now at least you do. So we have a harness that comes with a research idea, go talk to a few other agents, thinks if the idea is good or not, and then go implement and then iterate on the idea. And if I go to show you a brief kind of how many ideas did we have, is this many ideas. If you want to navigate this slide, you have to start from the beginning where we told the model go bit AES, and then it have many layers of ideas where try to actually find an algorithm. This slide might not has that much useful information. This might have more. The model had around more than 3,000 ideas. Off of those, more than 2,000 of this actually applicable to the problem. Of those, around 200 were actually it was novel ideas, and of all of those things, only 4 get to the paper. So we spent a lot of compute, like you have to, and to kind of get to the paper. So maybe all of the things I showed you was mostly in the cryptographic, and I tell you. So one question that a lot of people have is maybe we are bad at crypto, and that's why we have these cryptographic results. And it might be true. I don't have a crypto background, so like something that impresses me might not impress anyone else, but we actually showed this result to actual cryptographic people, and they actually were interested in the results. But you might also argue maybe humans in general bad at crypto. Maybe, I don't know. But we actually not only look at crypto, we are looking at a lot of other security research, and which I have more background from, like network security, to do more like to go from to privacy and everything else. And we showed like we have actually promising results in all of them. We are spending most of our time verifying the results. And finally, what I want to kind of say, we used to say we need a novel and good idea at the same time, but as kind of we are showing that, and one of the beliefs was LLMs are maybe good at each, but not good at them at the same time, but maybe this is starting to move. Yeah, thank you. That's all.